Hello, in this video we will talk about music generation using PyTorch. So this is a deep learning task, and we mainly use the framework provided by MIT Deep Learning Lab. So you can search MIT Deep Learning Lab. There are two IPYMB files. So first, part 1, introduction, includes what is PyTorch and what is a tensor calculation step by step. Then we close this because we will focus on the second IPYMB and Python file. So this is called part 2 music generation IPYMB. And because this is the file I have loaded on the Colab, so it will use Comet Cloud to trace the learning process. But I get the API key, but this key does not work properly, so I download this file to locally, a Python source file. So this file will be explained in more detail. So I have set the working directory in my local computer. So you have to install PyTorch. You have to install PyTorch. If you have not done yet, you can go to torch.org to load to show how to install PyTorch. So the PyTorch is widely known that it's comparatively easier than TensorFlow and can do most of the job in deep learning. So after you have installed, you have to load this package first. It will take a while. Then we load this module, NM module, and optimization, all from PyTorch. Then we have to install. Before that, you have to create your environment in Python. So I have created our environment called MITDL with a Python version, for example, 3.12. Then I use counter activate MITDL. So now in this environment, then under this, I have to load this package. Now you have to install pip install MIT Deep Learning in this environment also. Then after you have done this, we can load so MIT Deep Learning package. So till then we have to load all these packages. Some of them not be used in this video, and I will not run this because this is not successful, but it's no problem for our explanation of the module. Then next you can assert if the CUDA works properly, it is okay. So in the process of installing PyTorch, you will install CUDA also, install Visual Studio, for example. So this will be another video. You can search from YouTube, for example. Then we will try to show the songs using MDL Lab 1 load training data. So there are 817 songs in text form. So in music data in Python, we have to usually will transform the music to the text. So this text called ABC file. So for example, all the music notes will be transformed to ABC file first. So this data has been transformed to ABC file, or we call it text file. So then, for example, we show the first song from MIT Lab. Then we can print this song. So this is a note file called ABC file. So all the notes are replaced with ABC and the number and special symbol. So this is the first song, and I cannot run this command in local environment, but you can try this in Colab. So in Colab, you can try this, play this song. Then next we have to join all the songs. So 817 songs will be joined into a very long string. So we call songs joined. Then we can show the length of this string, about 200,000. Then next we will bypass, because I have written this long string locally. So next time when you work again, you can just read this string file. Then next we have to create the vocabulary of this string. So use the sorted set function. Then we can bring the length. So there are 83 unique characters in this vocabulary. Then we have to create two functions, one called character to IDX, because we cannot just use this string in the deep learning, right? We have to transform this character, different types of these 83 unique characters in number. Then we can do deep learning. So this function called character to IDX does this job. And to contrary, we have to also create another function called IDS to character, because when the model gets the result of number, then we have to transform to text or to the ABC nodes. So these two functions. Why I have to use this Python file, not IPYNB, because part 2 music generation from MIT, they have many places called to-do job. So this is not a completed IPYNB. You have to test locally and do many hours job to fix this file. So next we can print, for example, first 20 ABC nodes. So you can see ABC nodes, their corresponding index. So 83 ABC nodes has 83 index from 0 to 82, right? And we show vocabulary again. This is vocabulary from ABC nodes. And next function called vectorize string. This is what I have said. We have to transform these nodes into IDX number first. Then we return an numpy array data object. Because you cannot just input a list to do machine learning. You have to do the tensor, but PyTorch tensor can transform directly from list to PyTorch tensor, but this is very slow. So best is to transform list to numpy array first, then use PyTorch to transform numpy array to tensor. So this function exactly transform lists of this. First transform ABC nodes to the numbers, then from these index numbers transform to numpy array. Then we can show, for example, using this function, so passing songs joined. Then we can show songs joined. There are 200. This is original ABC nodes for this. Then we vectorize these ABC nodes into number. Then next is we show the characters and mapped to the integer number, which is the index. And we show, so this Alex to this number, right? This is the first several ABC nodes, then modified to this index, which will be input to machine learning. So next, the function called get badge. So get batch do the job to return X batch and Y batch. So what is X batch and Y batch? So X batch actually is input index like this, but it is a batch. So we have a length, sequential length. So for example, sequential length is 100 and the batch size is 8. So this X will be a two-dimensional array with 8 and 100 in shape. And similarly, Y batch will be 8 and 1 in shape. So both are two-dimensional array. Then we will test, for example, vectorize 10 to, this is the batch 2 and 10 is the sequential length. Then we show X batch and Y batch or get batch with this input argument. Then we'll show the shape X batch is 210, correct? And we assert Y batch is 210. It's incorrect. Sorry, Y batch is 21, right? Sorry, this is correct. Correct. Then we can get one batch to test. So we set the batch size is 1 and sequential length is 5. And from the vectorized sounds, which is the 200,000 index number, 1, 2, 3, 4. Then we will show this batch. So you can see step 0. This is because sequential length is 5. So input number is 45 and expected output is 22, which is for this string, input is this string. So why we show this? Because in music generation we have a sequential length. What means sequential? Sequential length means LCM means that we will not focus on one note or one character, one IDX. We focus on 5 as a data input. So for example, if you have a long string 100, so we take first 5 as the input, and we take a second from the second to the 6th string as the output. So if we look at this, so this IPYNB file will show you what is the LSTM. So LSTM, this is the sequential length. So this is the five nodes with 5 index. So for each index has output, but this is the model part. So anyway, from each input, what is the input? Input is the IDX odd nodes before in front of this one. So for example, this is the first node, this is second, and this is the 5th. Then for the second, we have input from first. Then output is the second. This is output. But between them, we have a state from this module. So state from previous state will have information from the long sequence. So the output of a second nodes combines the information of the first node's input and the state of the last 5 states. So this is called hidden state. This is the key information from this module. And this is one by one. So that's why we will have input of 5 sequence nodes, and output also 5 sequence nodes. Then input is first to the 5th, but output is second to the 6th, right? So this is the main idea of, because we set the batch is 1. Batch is 1. So this is the first batch. First batch has 5 input and 5 output. You can see in step 0, input is 45 and output is 22. And second step, input is the first output, right? 22, then output is 38. And the third step, input is 38 and output 58, and so on. Then next we will build this model called class LSTM model. Then this model is a sub model from PyTorch NM module. Then initialize, we have vocabulary size H3, right? Embedding dimension, because we have to transform all the features from each index with embedding size. Embedding is numeric and continuous numbers. This is very important. We cannot just training on index number. And hidden size is, if you look at this, the hidden size, this is not only one new row. This is a hidden size, for example, 1000 new row here, right? So we have to set 1000, for example. Then we'll initialize this attribute, and we will create the layer first for the embedding. Embedding input is vocabulary size. So each one of these H3 index will be transformed to the embedding number. Then second is LSTM layer. Input in embedding dimension, output is hidden size. Then the last is a linear layer from hidden size to the vocabulary size, because we have to use multinomial logic to generate the most probable nodes or the index from H3, right? So quite simple 3 layer. Then there are 2 standard function called initial hidden, because in the first node we have no state, so we have to initialize. And another function called forward actually is just to calculate from layer to layer, from cell banding, then LSTM, then FC out, then we get this out called logic. And if you want to return the state, you can also return the state value also. If not, just return the out. So create this class. Then we will define this number. So the vocabulary size, embedding dimension 256. So each character or each index will be transformed to the feature size of 256, and we set hidden size 1024 and the batch size 8. Then device set to GPU to CUDA. Then we create instance of this module. Then we can print this module. So next we can create a test XY get 1 batch. So from this original sounds 200,000 index number, we get a sequential length 100 and a batch size 32. Then successful, and we set both to GPU to the device. Then we can use predict is the module X. So module X, if we run this module, because this module is instance of this LSTM module, right? Because we have created this module. module. So we just run this module and input. It will automatically run the forward, run all this and to the forward, and it will return out. Then we will show the input shape. Sorry. So input shape is 32, 100. So 32 is the batch size, and 100 is 100 index. So this is sequential length, same as this is two-dimensional torch tensor. And we print out the predicted. So the predicted is three-dimensional torch tensor. 32 batch. The second dimension represents 100 sequential length of these nodes. Therefore, each node has 83 largest number, right? Because we have to choose from this 83. But this is not probability. From this, you can calculate the probability, but we show later that we do not need to transform, which we will include it in the code. So just note the output is three-dimensional and input is two-dimensional. Then we can use multinomial or softmax to get the sampled result for this batch. Then we can show and the sample index. $100. This is the 100 nodes. So this is for the result for each. Because this is for the first, or we say the first from this batch, and this batch, the first sample from this batch includes 100 nodes, and this is 100 output. And we can also show the next character from these nodes. So from this index to the nodes, so these ABC nodes, or we will get the result exactly like this. This is the result of what we will expect. So next, after we have created the model, we have to define the cross entropy for the loss definition. Then we'll calculate the loss. So the loss actually is between the batched label and batched logits. So label, we get each batch two-dimensional data, and we have labels. Labels actually is the Y value, right? But we have to use the view function to make these two same dimension. And the batched logits actually is the logits just the output number. Then we also have to transform them, use the view. So between these two, we'll use cross entropy, we'll get the loss. Then next we can show the Y shape. Y is digit for 32 batch and 100 output sequence number, right? Then predict the shape. After this is three-dimensional, so 32 and 100 and has logits. Then we can calculate the loss. So this is the prediction shape, sorry. And this is the loss. one scalar number. Then we will go to the formal training process, set the vocabulary size, and we set the parameter, hyperparameter for the training, embedding dimension, learning rate, and 3000 iteration. You can also set the checkpoints, save the module locally. So next we will bypass this code because this is used for Comet API for the experiment. We will not use this locally. Then we create a model again. Then we set the model to device. Then we set the optimizer using Adam. Then define a function called train step. So for the train step function, we'll set the model in the train status. Then we optimize the zero grad. This is a very standard statement in PyTorch. Then we use y hat from the module x, which calculated from the forward function in the model definition, right? Then we calculate the loss and use loss backward. This is also standard and optimizer.step. This is statement are standard in the PyTorch module. Then we create a history for show the results and use this to show the bar. TQDM package for show the bar. Then set an iteration for train this module. And you can see we also comment out experiment because we will not use this locally. So in the training process, we'll get X batch, Y batch in each iteration. Then we set train step for this X and batch. This is a function we defined earlier. And the result is, and we use history append the loss and plot this loss just to do it, right? And in the end, we will save modules state in, you see, very quick. My computer has a GPU RTX 30, 6J. Actually, you need 1000, for example, is enough. In the iteration is enough. So finished. Then, for example, we can save this module. The next we can load this if we want. So next job is to generate new text, generate new music notes, right? But we have to set module to evaluation status because we do not want module to update parameter in this stage. Then we define a function called generate text, and with this module, and we set several start string, and we set a generation length 1000 index or notes in the new music. Then inside of this function, we will first get this length of the start string, then we will vectorize, because this string is ABC nodes, so we'll vectorize to the nodes, to the numpy array. Then text generated, we will use this, because this first string we called text generated. Then we append one nodes one by one to 1000 of length, right? So first we will put this first start string to called input index, and we transform to the list, because in the end we will transform to string. So we transform to list to this text generated first. Then we will use this input index and transform to the tensor, because the module input is the tensor, right? And we also will create a state, use model initial hidden state, then to the device. Because we have said that the prediction of the next index is based on the information of the previous index and the hidden state of the previous state with sequential length. So for example, we want to know the number 35 predicted nodes. So input is the number 34. These nodes. Actually, this is also predicted in the previous stage, right? So we have predicted 34 nodes, and as input to the number 35 we want to predict. Then we have the sequential length of all the states which is defined in this module. Sequential length is 100. So we have also to create this state with the length of 100, right? So hidden state. Then this information will predict the number 35 nodes. So in this stage we have to set input is the last nodes from this first input, because we have created these states, right? So get this first one, and next we go to this range or the iteration for the 1000 nodes, but we have to minus this start length, because this first string we have put in the generated text, right? Put in the generated text. So for this string, for example, 10, so we just generate 990, for example. So in this iteration, the first is use the last from this input string, and we will use unsqueeze to same dimension for the module input. Then we use prediction and state is the output of this module as the input from these nodes. Then return state is true, we call, because we want to use this state. Then from these predictions, we also will transform to the dimension, one dimension less. Then use the multinomial softmax first, get this index number with the output. Then we also use string and transform to this append to text generated with 990 generated. In the end, we will return this text generated. So this generated text function is a little complicated. So we can call this function and with the input. For example, input is this string, these are music notes. This is generated process. And we will also use, because this is generated, you can see like this. This is a list, right? With 1000 ABC nodes, right? but we have to concatenate all these items from list to a long string. So we use join and string for any generated list comprehension. Then we show again. So now this is a long string with 1000 ABC nodes. So we will not go further in this video because next job is to transform these ABC nodes to music file or MIDI file and further to, for example, MP3 or WAV file. But we don't show this here. You can, because this is also very raw. You have to do some further job. But in our video, I think the most of the machine learning job is done here, right? Hope it will be helpful if you want to know something about the music generation using PyTorch. Actually, this is quite similar as text generation. Exactly the same, right? Exactly the same if we get the text as the input. So hopefully it will be useful for you. Thanks for watching.